All right, what is up, Calculus 2? It's good to see you. I am here. I am going to work through a practice gateway number 2. So on my computer here, you can't see it, but in the background, I have pulled up a practice gateway exam, and we're just going to work through it. We'll probably do this in 2 videos, doing 3 problems in each. I'll go a little bit slower than if I were just doing these on my own. I know you only have 30 minutes to take the actual exam, but I might take a little bit longer here to go through some explanations and things like that. Okay, so the first problem that I see is this integral of 4x root x squared plus 13 dx. Maybe the other thing that I will add is that I haven't done these problems yet. I just pulled them up, and that's because I want you to work through them with me. So maybe I'll make mistakes along the way, but I'm hoping for you to be able to explain my thought process as well, so you can actually watch how I think through these things. So I'll kind of think aloud here. In particular, as I look at this first problem, my first instinct is to try to do a trig substitution. Why do I think that? Well, I think that because I see this square root of x squared plus 13. That kind of thing, whenever we have like a square root of x squared plus a squared, that oftentimes lends itself to a trig sub. However, in this particular case, the more I look at it, so before I dive into that, another thing that I notice is that I think we can maybe do this a little bit easier, and here's how. I notice that if I make my u x squared plus 13, right? So another thing that I thought about here was doing a u sub. If I make my u, this x squared plus 13, this stuff under the radical, then my du becomes 2x dx, which is great because notice that what I have sitting outside of the radical is this 4x, right? So this tells me, in particular, if I multiply both sides of this by 2, this tells me that 2 du is equal to 4x dx. So actually, if I make this u substitution, I can think of this, right? We can rewrite this as, okay, so 4x dx is equal to 2u. So I'm going to get a 2u times, and then this root x squared plus 13 just becomes root u, which is the same thing as u to the 1/2. So I get this. Okay, so this becomes the, I'll bring the 2 out front. I get 2u to the 3/2 du, right? If I have u times u to the 1/2, I'm going to add up those exponents. And now this is something, excuse me, I wrote 2 twice. So I pulled the 2 out. So this 2 is gone now. So now I'm going to take the antiderivative of that u to the 3/2. So I'm going to get u to the 3/2 plus 1 gives me 5/2. And then I need to divide by that new exponent, which is 5/2. Don't forget my plus c. Let's clean this up a little bit. So I get, so dividing by 5/2, right? Dividing by a fraction is the same as multiplying by the reciprocal. So that's the same as multiplying by 2/5. So 2 times 2/5 gives me 4/5. And then u, right, we have to undo the substitution because the problem started with x's. We're also going to need to give our answer in terms of x. So I'm just going to replace this u with this x squared plus 13. So 4/5 times x squared plus 13 to the 5/2 plus c. There we go. Maybe I should take a moment. Okay, we'll probably see another trig sub problem later on, but maybe I will make a remark that if you wanted to try this using trig sub, you totally could. I don't think I'll work through the whole thing here, because I do think this solution is probably a little bit easier. I think I think of trig sub kind of as a last resort, because as you've surely seen, it can be a little bit more complicated than some of the other strategies. But I think if we wanted to do that, so this x squared plus a, right? So this x squared plus 13, this has the form x squared plus a squared, which tells me that I'm going to want to use the identity tangent squared x tangent squared theta plus 1 is equal to secant squared theta, right? And so because this is a 13, right, because this a squared in this case is a 13, the substitution that I would want to make here is x is equal to the square root of 13 times tangent theta, because then, if I do that, then x squared plus 13 is going to be 13 tan squared theta plus 13, which if I factor 13 out of that, then I get 13 times tangent squared theta plus 1, or 13 secant squared theta. Okay, so there's more that we would have to do, but if we wanted to approach this using a trig sub, that is how we could get started. Again, I imagine we'll see a trig sub problem somewhere else here along the way, so we'll work through one in full detail, I'm sure. And again, I think the u sub here is the easier strategy, but you could have also done it that way, I think. All right, problem 2. Let's see what we've got here. We've got, speaking of trigonometry, not quite a trig sub maybe, but we've got a sine to the 5th of z dz. Okay, so that's what I've got here. So what I'm going to do is, because this is an odd power, I'm going to split this up as follows. This is the same as sine squared z times sine of z dz. And now sine squared, this is 1 minus cosine squared. 1 minus cosine squared of z. 1 minus cosine squared of z. And then I still have my sine of z dz out here, right? So I just replace each of these sine squareds with 1 minus cosine squared. And notice, so because this was an odd power at the beginning, we're going to have this leftover sine of z sitting out here, right? We can group it in terms of, right? We've got a sine squared, but because this is an odd power, if we try and group things like that, we're always going to have this extra sine of z sitting out at the end. What does that mean? Well, that works out nicely because now I can do a u sub in which I set my u equal to cosine of z, in which case my du is negative sine of z dz. So why do we care, right? Again, I keep emphasizing that we have this extra sine of z out here. The reason that's so important is because now this sine of z dz, right, this part is just negative du. So this integral becomes the integral of 1 minus u squared, right, because our u is cosine, times 1 minus u squared again. And then that sine of z dz, like we said, that's just negative du. So I'm going to just go ahead and stick that negative sign out front and put that du over here. I'll pause and get a sip of water and let that sink in. Let you take a look at the bookshelf in my apartment. Okay. Now, where are we going to go from here? Well, from here, now this is something that we can work with much more nicely. We can go ahead and FOIL this out, and we're just going to get a nice polynomial. If we do that, we're going to get 1, and then I'll get a minus u squared and another minus u squared, right, by doing my foiling. So I'll actually get minus 2u squared. And then I'll get a plus u to the 4th du. So this becomes negative. Okay, now when I antidifferentiate, antiderivative of 1 is just u. Antiderivative of 2u squared. So I'm going to raise the exponent by 1 to give me u cubed and divide by that 3, that new exponent. And similarly over here, that's going to be plus u to the 5th over 5. So all of that has a negative sign. So I'm going to kind of do two things in one here. I'm going to go ahead and distribute that negative sign to everything. And I'm also going to undo my substitution. So this negative u that we're going to get, right, that's going to become negative cosine of z. Remember, our u was cosine. So now I'm going to get a plus 2 cosine cubed of z over 3. And I'm going to get a minus, right? Remember, we're distributing this negative sign here. I'll get a minus cos to the 5th of z over 5, and of course, plus c. I've heard that whenever you're on web work, you want to make sure you're taking the actual gateway. You want to make sure that the c is capitalized. I've heard that web work doesn't like it if you put a lowercase c there. So whenever you put your plus c's at the end, make sure that they are capitalized. In reality, in theory, it doesn't matter because c is just an arbitrary variable. But, you know, my beef with web work notwithstanding, you should make sure that you do that. Okay, great, great, great. So yeah, like I said, one of the key things to notice here is that this was assigned to the 5th. And so because of that, we're able to do this nice u substitution because we had this leftover sign. It'd be kind of the same idea if we had a cosine to the 5th. There's a few variations of this kind of thing that you can see that work out kind of nicely. Maybe one thing I'll take a quick aside and just briefly show how you might do. So if we had an even power, I'll just show one example. So let's say we were integrating sine squared of z dz. Well, what we're going to use here is we're going to use a trig identity. So there's 2 of these trig identities. So sine squared of z is equal to 1 minus cosine of 2z over 2. Okay. Cosine squared of z has an eerily similar formula. It's 1 plus cosine of 2z over 2. Okay. So these identities are very important whenever you're integrating even powers of these things, of sines and cosines. Maybe I'll change the color here just to emphasize. I don't know, we'll go with green here because these are good. You should go with these. I don't know. So you'll notice these two formulas look very similar, as my Math-152 students know. I've said it several times in class. The trick that I use to remember which one is which is I remember that the cosine formula gets a plus rather than a minus, because the cosine formula naturally should have more cosine in it. That's a silly way to think about it that my Math-152 students are sick of hearing me say. But hopefully it'll help you remember this. So if we were to try and integrate this sine squared of z dz, I'll just show this real quickly. We'd integrate 1 minus cosine of 2z over 2 dz, right? So I'm replacing this sine squared with this 1 minus cosine, that formula that we just talked about. From here, notice that this is the same as the integral of 1/2 times 1 minus cosine of 2z dz. And in particular, that means that I can pull this 1/2 out front. Oh, I don't need to see my video on there. Right, so 1 minus cos of 2z dz. Okay. Now this becomes 1/2. Okay, the antiderivative of 1 is just z. Now, okay, so let's actually go ahead and I'm going to work through this integral here in 2 ways. Okay. Or maybe I'll work through it one way, but I'll explain it in 2 different ways. This integral of cosine of 2z. So one way that we could go about this is we can say, okay, let's let u be 2z. So then du is just 2 dz. So what that means is that dz is equal to 1/2 du is equal to dz, right? So in particular, I'm just going to focus on this integral here. So this integral becomes the integral, I'll do it this way. The integral of 1/2 cos u du, which is the same as 1/2 sine, and now our u, I'm going to go ahead and just undo our substitution here. Our u was equal to 2z. So we get that. So notice in particular that basically what ends up happening is we have to divide by 2 because of this 2z, right? So because of the 2z inside of cos, we must divide by 2, right? That's where this 1/2 is coming from. So another way that you can think of this, which kind of gets you to the same place, but maybe a hair quicker. Another way to think about this. Another perspective maybe to differentiate cosine of 2z, we must multiply by 2. Because of the chain rule, right? Because the derivative of this 2z on the inside is 2. So when we take the derivative of cosine of 2z, we have to multiply by 2 to account for that. So kind of, if you think about how do we do this in reverse, right? When we're doing antiderivatives, to anti-differentiate, well, what's kind of the opposite of multiplication? What's the opposite of multiplying by 2? Well, we have to divide by 2. Okay. So all of this, what is the point of all this? All of this is to say, right? So if we start here with our integral, if we come back down and continue, we get our 1/2, we get z minus, and now this integral of cosine of 2z dz, well, the integral of cosine is, or the antiderivative of cosine is sine. So this is going to become sine of 2z, but now I must divide by 2 plus c. So again, what was the point of all this? Kind of two ways of seeing how we get this divided by 2 here. The second way is a bit more intuitive, where I kind of walk through this perspective. This way up here with the u-substitution is a bit more rigorous, right? So that's kind of showing you more formally where it comes from. Whereas at this point, because I'm an old man who's done a million of these, I tend to think about it a bit more intuitively, and it comes a little bit more quickly once you've done it. Okay. I hope that makes some sense. If you prefer to think about it using the u-sub, that's fine. If you prefer to take this intuitive kind of explanation, that is fine as well. In any case, that is how we would do that. Okay, that wasn't even one of the actual gateway problems. That was just some good stuff, I think, though. Some good stuff to talk about along the way. All right, next up, problem 3 on my gateway here is 1. So we're integrating 1 over x root x squared minus 25 dx. Okay, so my first thought here, okay, maybe I shouldn't say my first thought because I know what I would do. However, one thought that one might have might be to approach it like problem 1. Approach like problem 1. So in problem 1, what we did was we said, oh, look, if I make u x squared plus 13, then my du is already sitting out here. Well, kind of, you need to multiply by 2, right? But basically, my du is already sitting out there up to a constant multiple. And you might think kind of the same thing here. If I set u equals to x squared minus 25, well then, hey, du is 2x dx, and would you look at that, I've got an x sitting right out here. However, the issue with this here, the reason this doesn't quite work is the following. The issue is that, all right, so this tells us that 1/2 du is equal to x dx. But what's going on here, the issue is that we don't have x dx inside of our integral. We have 1 over x dx in our integral. Right? Because this x is in the denominator. Right? Because x is in the denominator. So unfortunately, this idea that we have isn't going to quite work out like it did up in problem 1. Fortunately, there's another strategy that we can use. It's everybody's favorite. Maybe I say that somewhat tongue-in-cheek, because I know that this is one of the more challenging strategies that we've learned, but we can work through it. We are going to want to use a trig sub here. Okay. And so let me take a minute to I want to take a minute to talk about trig sub more broadly before we apply it to the specific problem here. So trig sub, it all kind of starts, the idea behind trig sub all kind of starts with this identity that sine squared plus cosine squared is equal to 1. I don't know about you, this is my favorite trig identity because it's the foundation of so many others. Okay. In particular, what does this tell us? This tells us that cosine squared of theta equals 1 minus sine squared of theta. Okay. Now, if I take this original identity, this sine squared plus cosine squared equals 1, if I divide both sides of this equation by cosine squared, well, sine squared over cosine squared is going to give me tangent squared. Cosine squared over cosine squared is going to be 1, and 1 over cosine squared is going to be secant squared. Right? And so from this equation, we actually get two other identities. One of them, I'm just going to take what we just put, I'm going to rewrite it. And in a minute, you'll see why I'm rewriting it like this. Right, so I'm basically just flipping the order around the equation. So secant squared is tan squared plus 1. On the other hand, if I subtract 1 from both sides, right, so if I bring that 1 over there, then what do I get? I get tangent squared is equal to secant squared theta minus 1. Now, notice that if you this is said a lot in sports, in like sports radio talk. I listen to lots of baseball podcasts. If you squint and if you squint your eyes and you look at this and you kind of think about it for a second, you'll see perhaps a connection between these two equations. Let me use a different color. Let me not use a Clemson color. Between these two equations, right? Maybe actually, let me just draw the arrow one way. Right, so if I look at the trig identity on the left-hand side in this box, if I look at this column, right, if I look at these identities, they look very similar. If I look just at, actually, let me even focus on, let me just focus on this part even. I think this part even. This first one, this 1 minus sine squared of theta, well, this 1 is just a constant, right? Like a squared is just a constant, minus some function of x squared, right? Minus something with a variable in it squared. And same thing here, right? This sine squared of theta is some function of a variable, in this case, theta. Right? Similarly, this tan squared plus 1, well, this is some function of theta, right? So there's a variable in here, and kind of the same idea here, right? There's a variable in this x squared plus a constant, and same idea in this last identity. So what this is, so the reason I write this out is that these identities are going to inform our trig substitution. So, for example, let's come back to our actual problem here. We have this integral of 1 over x times the square root of x squared minus 25. This x squared minus 25 has the form x squared minus a squared. And in particular, our a here is 5. So this tells me that my substitution, I'm going to use this bottom. I'll write it over here. So this tells me that I'm going to use this bottom identity because this has the form x squared minus a squared. So what do I want? I want to take, yeah, I will write it over here. So I want to define x in such a way that x squared is equal to 25 secant squared. Because if my x squared is 25 minus secant squared, then I'll be able to factor out a 25 from both terms and use this identity here. So if I want my x squared to be 25 secant squared, that tells me that I want my x to be 5 secant of theta. Okay. Now, if x is 5 secant of theta, then my dx is going to be 5 secant theta tangent theta. Theta. Okay. And so I'm going to go back to my original integral. I'll go ahead and write everything out here. Okay, dx. So now, first of all, I'm going to replace the dx here with 5 secant theta tangent theta. Theta d theta all over. Now, in my denominator, my x is 5 secant theta. So 5 secant theta. And then this root x squared minus 25 becomes root 25 secant squared theta minus 25. Okay. So I've just done a substitution. Let's keep going. So first of all, so now I can start to cancel some things, right? The 5s are going to cancel here, and so are the secant thetas. So I'm just going to get tangent theta, d theta up top. And on the bottom here, well, I can factor a 25 out from both of these guys under the radical. And I get secant squared theta minus 1. Like that. And actually, just a moment ago, we saw that secant squared of theta minus 1 is tangent squared. So what does this become? Well, the square root of 25 is 5. And then we have a root tangent squared of theta. So this actually just becomes the integral of tangent theta d theta over 5 tangent theta. So we get these tangent of thetas cancel, and I'm going to go ahead and move the 1/5 out front, and I just get the integral of d theta. Okay, my gateway exam is yelling at me that I'm running out of time, but that's okay, because here I'm just focused on explaining everything in great detail. So this just becomes the integral of 1/2. This just becomes 1/2 theta plus c. However, we're not quite done, because just like when we did our u sub, right, the problem started, the integral we were given started with the variable x. Okay, now Zoom is yelling at me that my meeting will end soon, but I'm going to have time to get through this problem. The problem was given to us in terms of x, so our answer needs to also be in terms of x. So how do we do that? How do we figure out what this integral should be in terms of x? Well, we know that x is equal to 5 secant of theta. That's how we defined it. And we can use this to solve for theta. So if I divide both sides by 5, I get x over 5 equals secant theta. And now, if I take arc secant of both sides, the inverse secant function, then I get arc secant of x over 5 equals theta. And so my final answer is 1/5 fifth arc sec x over 5 plus c. There we go. I think that will do it for this video here. I hope that you find this helpful. I will go ahead and do a part 2 with the final 3 problems. Looks like we'll get some more trig here. Looks like we'll get some integration by parts maybe, as well as some partial fractions. So looking forward to seeing you in that next video if you like. Again, I hope you found this helpful, and good luck on Gateway 2.